very quickly whiteboard, because really the problem is, oh sorry, what is this? Disconnect. Can all of you see the whiteboard?
Yes,
and hear me?
We can.
Right. So, really, in a sense, the practicals that we are now going to do are, in a sense, not really practicals. They are more of theory as well. But I would like to call them as practicals because they will now deal with the three most important components of all this teaching theory, which is the application of this theory to actual practical situations, preferably in industry. So really, the way I am going to divide these three practicals, I don't think we can do more than three, and these will be short practicals. And these will require actually you people doing less of practicals and more of the theory, but applying the theory that you have learned. So in the first, and we will actually move in the first, we will actually be moving backwards. Essentially, in the first, you will, I mean, and we are going to do immobilization because almost all of industry uses immobilized enzymes. I mean, you can't afford to use non-immobilized enzymes, you have to reuse them. So in the first, we will do immobilized enzyme kinetics, and I will talk about that today. That is one. And so we will do the whole thing. We will do forward and backwards. We will make assumptions of kinetic parameters, Vmax, Km, and actually Km approximate, the observed or the Km apparent, and its relationship to R, and its relationship to dE, diffusivity, and so on and so forth. Do you remember all these things that we have taught you till now? And so you choose numbers, and then we will sort of derive the velocity equations as functions of substrate, as functions of time, product velocity versus substrate, product versus time. These are the things that you have to predict. And after you have predicted this, you then move backwards, choose points here, and run the whole experiment backwards by choosing these points and then deriving these parameters from this data. So that way what one is trying to do. One is trying to move forward from the parameters to P versus T data, and from the P versus T data backwards then to the parameters of the system. That is number one, that is today. And next class, if we possibly, we will do the error analysis. And I do not know whether you are familiar with error analysis. Most of the time you will say yes, but I really am not very confident about it. And the whole logic of least square, etc., etc. But essentially minimizing error. And obviously you cannot apply least square straight away on non-linear functions. And so really it is called parameter estimation. And so you have to make guesses as to whether you are assuming, I mean, and these are the parameters that, so essentially you have a black box. Okay, gone again. Essentially you have a black box, and these are the parameters, Vmax, Km, etc., and R radius and all that. And this is your input time maybe, and whatever substrate concentration, and your output is product versus time. And how these parameters then determine this profile. And from this profile of T versus P, how do you estimate these parameters? This is your black box. This is your model. And this model may or may not be linear. And the data that you have, the error may be proportional to P. The error may be, so you have to write the model as if it is an overfitted model, because obviously it's an overdetermined system because you have only 3 unknowns, but you have 20 different possibilities of P versus T. So obviously P versus T, if you have 1, 2, 3, 4, 5, 6, 7, 8, and so, so if you have 4, 5, 6, 7, 8 data points, then I can choose any 3 and determine 3 parameters, any 4 and determine 4 parameters, and so on and so forth. But if you have 8 parameters, then you have to choose all of them simultaneously. That is the whole logic of overdetermined systems and essentially regression analysis, right? After all, you don't fit a line by choosing 2 points, and these 2 points, so these 2 points will fetch you somewhere here, these 2 points will fetch you somewhere here. So you don't fit all kinds of graphs, you just fit one straight line through all the points, where the points are in least square sense. So obviously P has an error associated with it, and now you have to minimize error. But is it P plus E? which is a fixed error, or is it P1 plus E, which is, or is it P1 plus E, which is proportional error? So is your error proportional to your measurement? Is your error a fixed amount with respect to your measurement? These are things, and then you minimize E. So this E minimization and this E minimization will lead to different kinds of, differentiation equations, where E has to be minimized from the basic model. So that is what we will talk about in the next class. And in the third class, we will talk about design of experiments, DOE, and how it applies to enzyme parameter estimation. So actually, ideally, I should have talked design of experiments first, then curve fitting, and then actually plotting. But since you're familiar with this, we'll go backwards, and we will start with immobilized enzymes. And what we will do is we will use the equations that you have learned in class. You have to take values of V, Km, and all of you should please take, and your practical class is essentially almost like a tutorial. The reason I'm doing this tutorial, or rather, instead of the practical classes, we have covered most of the things. I don't want to cover new things and confuse you further. Many of you have said we should cover more stuff, but I don't think the feedback in terms of grades and marks are matching with your demands. So we should do this in a solid way. So all these parameters that we have developed, let us go and look at it in industrial, actual practical setting, determine parameters, take the parameters as given, plot the graphs, and then do the reverse. So this is simulation, simulate the P by T using these values, and from the P by T determine these values. And then of course later on we'll talk about analysis and what points to choose, how do you perform the experiment. So really it should have started like this, gone here and gone there, but I'm sort of going backwards because this is what I have taught you already. So let us start applying it. Okay, so let us begin by the immobilized enzyme kinetics, and you know how it is done in industry. I mean, I sort of mentioned it very briefly, but essentially the idea is simple enough. First, and there's 3 stages it is usually done. First, you run a batch culture. You run batch culture, and the batch culture is run with free enzyme. And let me not take complicated enzymes and make life difficult for you. Let us say it is A going to B, and not even reverse, CV is equal to Vmax S upon Km plus S. Let us take the simplest. Though usually nowadays most industries are mostly keen about reversible reactions, because most of the enzyme in the industry is now being used for transformations, steroid transformations and drug transformations, chiral transformations. These are the things that enzymes are best being used for, and almost always delta G's are very small, so the reverse reaction becomes important. So this equation is not really correct, but I mean, I have already asked you a question on reversible enzyme kinetics. Let us keep it at this. So you run a batch culture, and so the first job that you have to do is predict P versus T in a batch culture, given different starting substrate concentrations and different starting enzyme concentrations. Remember, Vmax is actually K2E0. So different amounts of enzyme will fetch you different graphs. So really the point is that time versus P is the graph that you have, and you have to predict this from this, and you have to show me these graphs. And so on and so forth. These graphs are maybe different S values, S initial values, in a batch culture. Remember, in a batch culture. So you have to predict these data points, and this is something which you have already done. So it's a very preliminary exercise. You have done this already. It is essentially the integration of this equation, right? So it is actually ds by dt is equal to minus Vmax S upon Km plus S. This is equal to minus. So, essentially, that it's Km plus S ds. Remember, it's batch culture, ds upon S integral is equal to, with a minus sign, of course, is equal to Vm integral dt. And so, given and this integration is rather simple, and so you have to predict P versus T graphs. And from the P versus T graphs, now you can choose data points, and you can have different starting S0. So T is equal to 0 to T is equal to T, and this is S0 to S. Now different starting S0 values, how these graphs look like. So obviously you can very clearly make out that the red has a lower starting S naught and the green has a even lower starting S naught. Right? And then with different amounts of enzyme, which means really Vmax changes because your K2 E naught, this is K cat, but you can change the amount of enzyme and find out different reactions. But that really is not very relevant because it is Vmax increasing. So this, and of course the way the you know, they have taught to you is that you should take the initial slopes and use that initial slopes to calculate dV by ds at S naught. But that's not a very accurate method. You can take initial slopes, and that is dP by dt, that is ds by dt, that is ds by dt when the substrate has not been utilized. So this is actually V at S is equal to Vmax S initial and Km plus S initial. And so different S initial values, a double reciprocal or a Hales plot gives you Vmax and Km. So that is job one, which is something which you have already done, but for completion's sake, you should do this. So most people take a batch culture, run a batch culture with different enzyme concentrations and plot the profiles. And from the profiles, they tend to determine what the hell is happening to what is the Vmax and Km values. Do not run it for too long because when substrate gets exhausted, really makes no sense, because please also remember that this is P, but the values of S are actually going like this. And different starting values of S. If you start here, then of course it will go like this. Whatever. So these are the points that I'm trying to make. These are different S values. This is for different enzyme concentrations. This is and different starting S values. And so it ends at different points. Is that all clear? All of you are familiar with this? This was just a revision. Hello? Can all of you hear me? Hello? Hello?
Yes, sir, we can hear you.
You can hear me? Yeah. I don't know why this is not working. What's wrong? Why is it jammed? I think I've had trouble with this. Can all of you hear me?
Yes, sir, you're audible.
Yeah. So this is not, no, this is what something else has come up. Where is the oh, where's the whiteboard? Here it is. Can you see the whiteboard, all of you? Yeah. So let us now come to the main point. That is that once we have so really what we have is Vmax and Km. I'll not come to one more point which I'm deliberately ignoring. I hope you realize what it is. Then once we know Vmax and Km, we then take this enzyme and we immobilize it in beads. We put this enzyme in beads. So once we put it in beads, now this enzyme will not go out. So we can actually now from the batch, we move to the CSTR. And there's a reason for it. I'm not going to explain it. I thought it was obvious because you can also do batch, but you know, CSTR is much more accurate. And the beads are now sitting inside here. They do not go out because the outlet has a filter which prevents these beads from going out. And so you have substrate coming in. Now it is SF or S feed, and you have an S out. Please remember that the concentration this substrate concentration is also S out. This is a CSTR. This is not a batch where the concentration of substrate is changing. It is fixed. It's steady state. Okay. And so now from this, and choose a particular value of R, a radius, choose a particular diffusivity, and choose and tell me at SF values like this, at different dilution rates, what is the S out? And therefore the reverse question, that if D versus say S at SF equal to, let us say, I should write, I hope you remember, let's say 100 millimolar. I should not write moles. And what is it at, say, this is minute inverse, and let us say 1 minute inverse, 2 minute inverse, 3 minute inverse, 5 minute inverse, 10 minute inverse, and so on and so forth. What is the S out? Given that we have the same Vmax and the same Km, but this is not Km apparent, remember, this is Km. Same Vmax and same Km as that of the original enzyme, so the bead has not got spoiled. And so, what are the steady state values of these time points? Now, can you do this? And then the reverse question, that given S out values at these different D rates, can you, given the Vmax and Km and assuming that they have not changed, determine what are the values of S out? From the S out value, determine what is the diffusion constants and the radius of the bead. Suppose the radius of the bead is given to you, and then what is dE? Hello? Yeah? No? Yes? Possible? So this is your job. Remember that in a CSTR, external diffusion, external or film diffusion is not relevant because of stirring. Film diffusion is not important. External diffusion. It is only internal mass transfer which is important in a CSTR. So you get rid of external diffusion problems or external film diffusion, but your internal mass transfer problems remain. So let me ask some simple questions. What happens when I put, okay, when I put twice as many beads, 2x beads. Suppose I have 1x beads and I put 2x beads. What happens to SF and S out? Obviously, it will fall by how much? Question number 2. What happens when I halve the dilution rate? So these are the questions. So when I put 2x the beads, what happens? And the reason we do CSTR is because we get steady state values. And that is where it becomes interesting. Till this point I have taught you, so you should be able to do it. And now comes the more interesting part in the practical, that as we run this and we have steady state values, then remember that for every dilution rate you have a steady state value. All the outlet S out is high at high dilution rates, and at lower dilution rates, as we go to lower dilution rates, there will be steady state, and this is time. So it's steady state. And then with time, it slowly starts rising up. What am I talking about? Rising up. S out, because P out starts falling. P out starts falling. Because S is going to P, but S plus P is a constant, remember. So P out, this value starts falling at steady state. And this P out fall or S out rise is actually the measure of thermostability, of operational stability. Let me call it not thermostability, let me call it operational stability of the enzyme. And this is very important to determine. What is the operational stability of the enzyme from plots like this? And of course, the operational stability is a function of temperature. So your enzyme sort of E is some E naught starting consumption, E pressure of, you know what, minus delta E by RT. So obviously at higher temperatures, it will deactivate faster. Hello? Can you hear me? Hello? Can all of you hear me?
Yes, sir. Your voice is coming.
Clear, right? Generally, I think the other people have switched on and left or what? I don't really know. Anyway, so the point that I'm trying to make is very complex now. Now, given this value, think of a situation where you have enzyme got deactivated by 50%. Will the product concentration fall by 50%? Say P out at a particular dilution rate was, say, S out was, let me call it P out at different dilution rates. Let us say at low dilution rates, P out was high. So let us say 50 from 100, let us say this was 100, right? So let us say this was 100 millimolar. And let us say at very low dilution rates, this was 90 millimolar. And here it is 80, and here it is 70, and here it is 60, and here it is 50 at changing dilution rates. Now my question is, if the enzyme is deactivated to 50%, will this 90 become 45? And 80 become 40, 70 become 35, 60 become 30, and 50 become 25? Or you see a pattern? So when your enzyme deactivates to say 50% or 10% or 20%, how do you track this deactivation from a data of the product profile drop? So your product profile here, P, is going to be a constant and then going to drop. Now this drop here is enzyme deactivation kinetics. Now if this drop is like this, what does it tell you about this equation? About this equation here? Because the CSTR, so first you do a batch, then you do a CSTR to determine the diffusivity rates as a function of R and determine what R you should use. And then you use the CSTR over a long period of time to determine enzyme deactivation kinetics. Because they want to know how long you can run these beads. Now remember that these beads may be less stable, but the impact on product concentration may not be very high. For example, if you are getting an output of 90 millimoles with starting substrate of 100, and you're getting 90, when the enzyme is deactivated by 50%, it will not become 45. It will become something like 70. But here at 50, with 50% deactivation, your product may not become 25, but it will be maybe 26 or 27. Do you realize why? So here, this drop will be not significant. So 90 will not become 45, it will become 60 or 70. But here, the drop will be almost the same at high dilution rates when you're measuring deactivation kinetics. And how do you use these graphs to generate, or how do you use this equation and choose a particular value of delta E and RT at a particular temperature? Of course, you do it at different temperatures. You can also get a value of delta E as well because you know the deactivation kinetics. So how do you then do the reverse? How do you plot product profiles changing with time to determine deactivation kinetics, and how do you use deactivation kinetics to find out product profiles? Given the fact that this is internal diffusion control, it is inside a pellet. So I hope you remember. Do you remember your equations for first order, zeroth order, etc., etc.? And the fact that I had got a root k term there into CAS instead of KCAS. So as k declines to half, this reaction rate will decline to root 2. Hello? All of you are not able to connect up whatever has been taught to what we are talking in the practicals. So that is why I want you to do this exercise. In the next class, we will actually do it for you, or Kshitij, I will help Kshitij to demonstrate it to you. Real point is that how do you, so first batch to find out Vmax Km, then the next CSTR to find out diffusivity values, and time course to find out deactivation kinetics. Can all of you hear me? And then finally, really that is really the hard part, which is then finally you actually then take these beads and bung them inside a column. And so you actually say, well, hold on, this is what my output will look like, P out will look like, given a certain amount of external mass loss, given a certain damp polar number. And this will change depending on the velocity, etc., etc. And this P out will change, which will drop in a certain way given my deactivation kinetics, which I have determined from the CSTR. So now in this PFR, actually you have both external mass transfer as well as internal mass transfer operating. The internal mass transfer parameters are determined by the so batch to determine Vmax and Km, CSTR to determine the Km apparent effectively for internal diffusion only, and plus deactivation kinetics rates, and then PFR for the actual experiment in the industry where you have all these plus external mass transfer. How would you know that you have no external mass transfer impact happening? How would you say that there is no external mass transfer problems in a PFR? Can you think of something? Hello? How would you prove that there is no external mass transfer, significant external mass transfer in issue in a PFR? These are the kind of questions that I'm supposed to ask you, practical questions. How would you know that this is there or not in a PFR? Any answers? Think about it. This is a difficult question, so I'll give you 5 minutes. And I'll pause and try to understand whether you have understood or not. But I think today I covered a huge amount of ground, primarily because I took the theory and dumped it into an industrial practical situation, which is what happens when sometimes you guys go out to the industry and you are asked the practical questions from the industry, and somewhere along the line the connect between theory and practical issues has been never explicitly stated, and so you find yourself at sea and you find yourself very embarrassed. So that is why I raised all the equations and questions, and I jumped from theory to practice, hoping that somewhere along the line you guys are able to make the connections. And making the connection without my prompting would be really the best thing that happens, because then you will be able to make connections elsewhere also.
Sir, can you define, sir, can you define what is the precise aim of this experiment?
The precise aim of this experiment is to be able to determine the parameters. It is parameter estimation from experiments. Determine parameters. So what are the parameters? K, Vmax, K, and under immobilization conditions, under industrially practical conditions, under immobilization and in ways in which it operates in the industry, using under immobilization, using batch, CSTR and PFR, because this is where the industry will run. This is for the determination of kinetic parameters for immobilization and deactivation kinetics, and this is for determining enzyme kinetics. So batch helps you determine Vmax and Km. That is job 1. CSTR helps you determine diffusivity, DE, right? And the phi values and the cot phi and all those things. Remember the phi values and therefore the diffusivity. I hope you remember the relationship between DE and phi, and also deactivation kinetics, which means delta E. See this deactivation kinetics. So deactivation kinetic parameters and the phi and the DE associated with immobilization. This is basic kinetic parameters, batch, Vmax and Km, CSTR, the phi values and the DE values and deactivation kinetics, and PFR for external mass transfer parameters, which is the Dampoler number. Please don't confuse DE with DA. Yeah? And so I was saying that because I'm not generating this data for you, it would be good practice for you to generate the performance of the batch and the CSTR and the PFR given these parameters, and then work way backwards. So generate tables essentially of P versus T under different conditions. That is all that you have to do, right? So in a batch reactor, suppose I say that the P is 0 at T is equal to 0, P is equal to 5 millimoles at T is equal to 1 minute, and then it is, 9 millimoles at 2 minutes, and then, whatever, 12 millimoles at 3 minutes, and, sorry, and for, sorry, 14 millimoles at 4 minutes and 15 millimoles at 5 minutes. Suppose this is the data. Using this data, can you now generate for batch culture Vmax and Km? Obviously you can. It's not a very difficult job, right? Oh no. Has it gone? Sorry, can you hear me?
Answer this VM and KM we have to find under immobilization conditions.
Yes, now we come to the more interesting problem, which is, has this screen disappeared? I think it has disappeared. Yes, come back. So this is, for example, P versus T for VM and KM. On the other hand, if you know VM and KM, you can predict P versus T as well. The other way around also you can do. Suppose I tell you that starting S0 in a batch is 100 millimolar and VM is given as some 10 millimoles per second, 10 millimoles per minute, and KM is given as let us say 10 millimoles again, some such number, or 20, choose some number. And given these values, you can predict P versus T. And from these values, you can find out PM and KM. So it moves backward and forward, and you have done this already in the case of batch reactors. Now I want you to do this for enzyme immobilized reactors, which is in a CSTR. What is the steady state output S value for different S input values, S feed, and what is S out, given that the VM and KM are this for the free enzyme, and I give you also the phi values or the DE values. Tell me what would be the output, and you have to also look at enzyme loading. How much beads? So you have to also consider how many beads have you put inside. 10 beads, 20 beads, 30 beads, 1 gram of enzyme, 1 mole of enzyme. How much enzyme is gone in? Because Vmax is really K2 into E naught. So in the case of, similarly, just like Vmax here was given to you, this Vmax will be given to you by depending on the number of beads that you put inside. You put double the beads, your E naught doubles, your Vmax doubles. But your reaction rate does not double. I hope you realize that.
So since we have to define the parameters under immobilization condition VM and KM, so we need to we need to get these values P and T 0, 5, 9, 12, 14, 15 and time 0, 1, 2, 3, 4, 5. So will you give these values or we have to
No, I think I don't want to give it. There is a reason I don't want to give it. There's a very serious reason why I don't want to give it, whether it's quiz exams or end semester exams or mid semester exams. I mean, everybody writes the same answer. You see, everybody writes SDS page was not visible because it was too dilute, and everybody writes it was too dilute and therefore you should cut it out and do ion exchange. They write word to word, the answers are same. It is very embarrassing because not only because it is wrong, but it's obviously copied. Now, for God's sake, choose different values. Now, if everybody chooses 10 millimolar Vmax per minute and everybody chooses Km 10 millimolar, then I know that you have copied it. Please choose different numbers so that I know that at least once in a while you have sat down and done this on your own. I am very, very cautious. I don't want to give numbers. I want you to choose and submit. It's not a big job. Please choose.
So how we will choose these values P and T 0, 5, 9, 12, 14, 15 and time 0, 1, 2, 3.
अरे आप उल्टा करिए ना, इसीलिए मैंने आपसे कहा, अरे भाई मैंने पहले कहा ना, आप पहले Vmax और Km चुनिए. Please choose any value of Vmax between 10 millimolars to 50 millimolar or 5 to 50 per minute. Choose any value of Km between 1 millimoles to 1 millimole to 20 millimoles. और कृपा करके मतलब अजीबोगरीब नंबर चूज करिए 23, 25, 28, 3, 4, 7 millimoles. And from Vmax and Km, generate P and T. Is that all right? Can you do that? Yes, all of you? Yeah. After you have generated P and T, and suppose these are the values that turn out at P and T from this value of Vmax and Km. Then take this as 5.1, 9.3, 12.2, 14.4, 15.1 as possible errors, random errors. And then using these values, plot and determine Vmax and Km and show that the same Vmax and Km appear again. Especially if you change these numbers by slight amounts. Is this clear? Now,
yes sir, yes sir,
this
yes
is
sir.
the first job. The first job is easy enough, this batch. Then for the CSTR, choose different values of phi and DE and R and the number of pellets that you have loaded. And then find out what is the outlet substrate concentration. Steady state substrate concentrations at different substrate concentrations input at two points at different dilution rates. So generate graphs at least say 3 graphs. Let us say you have to sort of generate graphs like this. T, 0.1, 0.2, 0.3, 0.4 minute inverse, 0.5, not too many points, 1, 2, maybe this. And S initial, say 100 millimolar. What are the outputs? S initial 50 millimolar. What is the output? That is it. So generate graphs like this. Now again do the reverse. Take this value and this value at 100 millimolar and determine that you can find out the value of phi and DE and so on and so forth. Vmax and Km are kept the same. Are you getting this question? And the third part is the most difficult part. If you can't do it, tell me. Which is then assume some external mass transfer and find out what is the PFR output. Sorry, I forgot. यहाँ पे deactivation भी आएगा. So I think it might require a couple of weeks to do it, but please start this and show me what you could do. And next week we discuss this after the exam. Shall we stop here? Have all of you followed what I have been trying to ask you to do? Or Kshitij, you want to take over? If there are any questions?
No, sir, I don't have anything to add.
Anything to say? But yeah, what about the others? If you have any questions, can you do this? I know you can do this. You do this first part, the batch culture kinetics at different starting substrate concentrations, VMKM. Can you do the immobilized enzyme part in a CSTR? From the equations that we have been giving you, yeah, you should be able to do it. Choose a R value, choose a diffusivity value, and find out the output of CSTR, steady state output. So these are algebraic equations, steady state output at different substrate inlet concentrations and at different dilution rates. Okay.
And so we have to choose the diffusivity value and R value same as we have chosen VM and KM.
VMKM सेम रहेगा और आप लोग डिफरेंट आर वैल्यूज चूज करेंगे 2 मिलीमीटर का रेडियस. प्लीज मेंटेन डायमेंशनल होमोजेनिटी. हाँ, ग्राम, मिलीमोल, आर मिलीमीटर, उधर मिलीग्राम, मतलब सब अलग उल्टा पुल्टा मत कर दीजिएगा, है ना. प्लीज मेंटेन एसआई यूनिट्स. ठीक है, तो अगर 1 मिलीमीटर डायमीटर चूज कर रहे हैं प्लेट का, तो वो अगर मीटर स्क्वायर में काम कर रहे हैं तो फिर प्लीज रिमेंबर दैट आर इज 0.001 मीटर्स. ओके. So make sure that you have dimensional homogeneity. If diffusivity आप लोग कैसे ले रहे हैं, मोल्स पर सेंटीमीटर ले रहे हैं या मोल्स पर मीटर ले रहे हैं, ये सब देख लीजिएगा प्लीज. Typical diffusivity values, let us see. You search out typical diffusivity values for enzyme immobilization kinetics, substrate diffusion through pores. Choose something. Let us see you do it. Okay. Can you do this? This is an assignment. Is it too difficult?
So we'll try and then let you know.
Okay, try and come back. I mean, as a matter of fact, you should try right now because this is the time till 5 o'clock you have this. Please try this. And the equations I have given you, the internal diffusion kinetics, the senior batch has the same equations. You people have it still with you? Or they are not attending at all? Well, so I want you to solve for, I mean, I don't want you to go all the way to the end for PFR external mass transfer because that's also a complicated integration. But let us leave that out because external mass transfer, internal mass transfer and deactivation kinetics in a PFR, there are very nice articles for it, but the algebra is rather difficult. If you can locate it and read it and understand it, I would be very impressed. Okay, so shall we stop here? And next 2 o'clock, next Monday, we meet on in the lecture hall physically. Okay, I will send you a message. Please inform your colleagues about the quiz followed by the lab mid-semester exam. Okay, and some of you have not submitted answer sheets. Now, today's lecture plus one more, which it is you are there. So have all of you submitted the old ones? I think 53 of you from batch, this junior batch, and only 25 from the senior batch. The rest, unfortunately, will not get any marks. And performance-wise, I am getting a bit worried. But yeah, that's really your choice.
Sir, can we possibly get an extension, for example, just until today?
On what? On the last set?
Yes.
Oh my, that went over last week. That was on the 6th.
Yes,
At least
sir.
you have not
We're really
do this
sorry
here.
that but a lot of us didn't submit, so it would be very grateful.
And what about the present one? What about the present set? Today's lecture and the one, I mean, there are still 2 more pending, right? Now, including today, or no, sorry, 3. 3 pending now, again.
Yes, sir,
right?
but the submission
3 more.
for the
So you
third
have
set
actually 6
come yet,
pending
right?
now. Yeah. So I'm going to put. What about the one which? So today's practical, last week's practical, and the last week's practical. Those 3 are also pending now.
Yes, sir, but the submission link for this set didn't come yet, right?
So we have groups of 3. This is the 3rd group now getting over. This is 9 practicals over now, right?
Yes, sir. Yes, sir.
Right. So you're now saying first you have submitted, second you have not submitted.
Yes, sir.
Second group of 3, and the 3rd group of 3 also is becoming due today. So you have to write something so that you can upload it.
Yes, sir. I will upload both the sets.
Okay. So all of you upload both the sets. I will give you a couple of days extension for the second set, and today's set has to finish, all the 3 has to finish by next week before the end semester, before the minor exam. Okay.
All right, sir. Thank you so much.
Okay. Fine. Thank you. So we'll stop it here.
This is the 8th experiment. Am I right?
Acha, 9th nahi hai. Sorry. Yeah, maybe this is 8th. So now these 2, the one which Kshitij has attended, these 2 of these. Yeah, sorry, you're right. 8th. So these 2 you have to submit by next week. And then we'll have 2 more, and that is it. 10. 10, 5 marks each, 50 marks, 20 marks for mid-sem, 30 marks for end-sem, 100 marks. For, of course, the junior batch, this 100 marks becomes 20 marks of your part of BBL433. For the senior batch, this 100 marks is your grade for the lab practicals.
Sir, can you tell the range of diffusivity and the phi? Like you told the range of VM and KM, so can you tell also the range of diffusivity and phi?
थोड़ा सा अचिंता ढूंढिए ना, थोड़ा सा ढूंढिए. Typical diffusivity values क्या है?
सर थोड़ा टफ है, तो अगर टीचर कुछ असिस्टेंस कर दे तो
ठीक है. आप कल के क्लास में मैं बता दूंगा अगर आप लोग नहीं बता पाते तो diffusivity. Tomorrow's class.
ओके सर.
थोड़ा सा आप लोग ढूंढिए. Okay, bye. Any other questions? Thank you very much. So let us stop this, and I am leaving you with this assignment. This is a pretty serious assignment, so might be difficult to do, but I would like you definitely to try.